to start with, I'm just going to introduce the idea by asking a simple question, which is, so think about a matrix A, a square matrix, an n by n matrix, all right? And over the reals, since we like to keep it real, and although nothing you're ever doing is really real, it's specifically real, like uniquely real. Like you could do the same calculation with the complexes or some finite field if you like. And the question is simply this: what criteria do you need for an n by n matrix to be invertible? So that's my initial motivating question. Motivating question for A and Rn by n, what criteria is needed for A inverse to exist? Now, of course, you're like, if you have good memory, then you know that we've already answered that question again and again and again, like 3 or 4, 5, 6, 7, maybe 10 different answers to that already, right, Chris? Like what?
It's the determinant has to not be 0.
Ah, that's the thing we don't know yet.
Because it would make things a lot easier when we're doing like homework and stuff.
You have read the chapter or are aware of it.
Or I know what a determinant is.
What's that?
Can I answer a question that does not reveal it using what we already know?
Well, yeah, you're in.
Yeah.
Yeah, sounds kind of.
All right, I'm going to go on then. Oh, well, I tried.
We save time though. We save a lot of time.
What I was looking for there was
2 by 2.
the columns of A are linearly independent. The rows of A are linearly independent. The rank of A is n. The nullity of A is 0.
That's a lot.
The linear transformation induced from A is invertible. The linear transformation induced from A is surjective. The column space of A is Rn. The null space of A is 0. The reduced row echelon form is the identity matrix. For every solution, if you look at the equation AB equals to B, there's a unique solution for each choice of B. These are all equivalent conditions that have nothing to do with determinant.
Is there a list of these in here?
Yeah, at the end of the chapter here, there's a list of 24 equivalent statements, of
That's
which I
awesome.
rattled off just a couple of them. Yes.
It's like isomorphic, basically.
It is true that A would induce an isomorphism else of A from Rn to Rn in this case. Yeah. Okay, so but none of these are something that you love, which is what? A formula. Right? Don't you like formulas when we take numbers and we put them into variables, we put
I
them
miss
together?
those things.
I
I
haven't
haven't seen one in like all semester.
I like making computers do those things.
Sometimes I miss them, and sometimes they frustrate me.
That's true.
They're much more tedious, much less entertaining.
Okay, so to start with, let's think about the 2 by 2 case. So I'll turn it back on in a minute, but it helps. You don't need to write this down. It's a drudgery to write this down, which is why I'm using the projector at the moment. Okay. This is motivational. This is not how we do problems in this chapter. Okay. Just give me about 5 minutes to try to motivate, and then I'll get to the actual how to do problems. Okay. So first of all, 2 by 2 case. We know that that's invertible. When it is invertible, this formula works, right? So for this formula to work, there's really just one weak link, which is this division by this number. In the case that AD minus BC is equal to 0, that corresponds to the case that the matrix is not invertible. All right? That in fact implies a linear dependence between the columns or rows of A. But you could also discover the need for that quantity by just doing row reduction, right? I could start with A. I could make row 1 and row 2 match up by multiplying the first row by C and the second row by A, right? Assuming that those are non-zero. Let's just assume that for the sake of motivation. Then you take row 2 minus row 1, bam, you get AC and AD minus BC. Of course, after this point, you can clear out the thing above using row reduction, but you see a necessary condition is that this thing is non-zero. We can discover that from row reduction in a special case, that A and C are both non-zero. Well, we can do the same thing for a 3 by 3 matrix, right? Where we don't have such a formula.
Hello.
So for a 3 by 3 matrix, it's a little more of a drag, but I guess the first thing I would do would just to be making all of the first column have matching entries, right? And I can do that by multiplying by either AC or BC or AC respectively for the different rows, make them match up, take the difference, that leaves the ABC in the top spot. And then I've got, I do the row reductions. Then I've got this. I figure out if I multiply well, what do? Oh, I divide by AE minus BB, assuming that's non-zero. That gets me a 1 that can clear these things out. If I can clear this out. And I just do row reduction, all right?
That last thing.
It would take me about 20 minutes of class to do this carefully. That's not really the point. The point is you can do this. And when you do it, you finally get this monstrosity in this entry, right? So in order for this to row reduce to the identity, which we know is an equivalent condition to it being invertible, I would need for this quantity and A to be non-zero. All right? So if you take that lovely quantity and you multiply it out, and you do, I have it here, you end up with, oh, come on, curses, I need that. Go away.
It's a double arrow.
Thank you. So you end up with this lovely quantity right here, right? It's 1, 2, 3, 4, 5, 6 terms. 3 of those terms have pluses, and 3 of those terms have minuses. And there's actually a very, very specific pattern that they're coming from the 3x3 matrix with. All right? And then, of course, A. So it turns out, right, that the sufficient condition for the 3x3 matrix to be invertible is actually for the thing in the square brackets to be non-zero. Okay? Guess what? The thing in the square brackets is the determinant of the matrix. And AD minus BC for the 2x2 matrix, that's the determinant of the 2x2 matrix. So the determinant not being 0 is, as Chris has spilled the beans, a sufficient criterion for the matrix to be invertible. And so here's the definition, in fact, for the first 3 cases. The 1-by-1 case is rather boring. Determinant of A is just A. Stupid. Determinant of 2x2 matrix is AD minus BC. This is the definition. And the determinant of A, well, this rather, why do I have AD? Oh, I did A, B, C, D, E, F, G, H, I. I don't know why I did that. I think it's because I started doing it. I don't know why I did that. Yeah. I don't think it's wrong. I just think I'm not sure why I did that. Huh. I want to show you something about this pattern before I put this away. Okay, so the 3x3 determinant. I think everybody can do the 2x2 determinant without a lot of trouble, right? But the 3x3 determinant, we're talking about the determinant of, let's see here, A, I'm going to do column, B, C, D, E, A, B, C, D, E, F, G, H, I, okay. One way you can remember the formula, this is a trick. I don't know how to tack this, so you'll have to look at this. So what you do is write the matrix, all right, and then write it again. I think that might be enough. I'm trying to remember. Well, I'm just going to write it again just in case. I don't know if I need to write it twice. I may only need to write the first, but we'll find out soon. So, so check this out. This is just a pattern, all right? So ADI, DHC, GBF, right? So that gives me AEI plus DHC plus GBF. And then, if you go the other way, as I'm doing in orange, those get minuses. Minus CEG, minus FHA, minus IBD. That, folks, is the determinant of this matrix, which I'll call A. Yeah, you see I didn't actually have to write. You see that? It turns out I didn't have to write this last column. Actually, I didn't even need to write that. this is a trick formula for the 3 by 3 determinant. I don't think it works for the 2 by 2 or even the 4 by 4. But it's pretty fast for the 3 by 3, right? So let me show you. Let's try it out. Let's calculate the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I do, let's see if I'm going to be lazy, I'll just write it again. 1, 4, 7, 2, 5, 8. Let's see here, so I do 45 plus 12 times 7 plus 12 times 8 is here. And the minuses are these ones, so minus 35 times 3 minus 48 minus 2 times 36 what's that? That's 12 times 15, right? $180 plus 45 minus 105 minus what, 48 minus 72, which is what, 225 minus 105 minus 48 minus 72, which is 120 minus, what's this? 120, which is, as you said, 0. Now, does anybody tell me why this is totally unsurprising that that's 0? Check this.
Matrix is not invertible.
How about this? 2 times row, 2 times, yeah, matrix is not invertible. That is, of course, one answer. How about 2 times row A minus row 1 of A? What's that equal to? Excuse me, minus row 3 of A. Yeah, sorry. What's that equal to?
Row 1.
Row 1. Yeah. So there you go. There's a linear dependence between the rows. Of course, there's a linear dependence between the columns too. Can you see it?
3 times column 1 is equal to column 3. Never mind, that line is complete.
Well, there's some dependence between the columns too that I don't know.
2 times column 2 minus column 1 equals column 3.
See if I believe. So that's 2 times column 2 is like 4, minus 1 is 3, 10 minus 2, wait, no. 10 minus 4, yeah, 6, sorry. 16 minus 7, yeah. Now, this is just, okay, that's like just a trick formula for the determinant. Let me show you, depends on the proof, I suppose. But there's another thing called the cofactor expansion, all right? The cofactor expansion for the determinant. And the cofactor expansion works like this. So if I have the determinant, I'll show you A, B, C, D, E, F, G, H, I. The way it works for the 3 by 3 case. Now, this is the expansion across the top row. I'll do that first. What you do is do A times the determinant of everything that's not in that spot. Okay, so like that's A, right? So you multiply that by the determinant of everything that's not there, not in the first row and first column. So E, F, H, I. All right. And then the other thing about the cofactor expansion is that this is alternating aspect to it. So it goes plus, minus, plus. So for the B, I do minus B. part of a cofactor expansion. The determinant of everything that's not in the column and row where B is. So basically the subdeterminant, which is excluded from the row and column where B is formed by D, F, G, I.
Actually, I have a question. Could that be a plus sign if you were doing the determinant of F, D, I, G?
Yeah, but I wouldn't do that. So this is the standard cofactor, just, So, okay, so plus C, the plus because we do plus minus plus, so it's C, and then you do the determinant of everything that's not in the C column and row, which is D, E, G, H. Okay? And these 2 by 2 determinants, you already know how to do those, right? So I could write that out, and I will, since we're starting. So that's like what? That's like A times EI minus HF minus B plus DI minus GF plus C times DH minus GE. And if you look at that, oh, we're not going to get the same pattern because I've labeled my matrix in the opposite
Oh,
way.
so it's not
It's
1 over.
It's the
EI
transpose of the other
minus
matrix.
HF?
What's that?
It's not 1 over EI minus HF anymore?
1 over.
Wasn't the determinant like the 1 over in 2 by 2?
In the 2 by 2 formula. A inverse is actually equal to 1 over the determinant of A. And then we do D, we do A, we do minus B, we do minus C for A equals to A, B, C, D. Now, I'm going to talk more about that next time. I will talk about the generalization of this formula in terms of something called the adjoint. That's where we'll talk about Kramer's rule, which I was exciting to the engineers. And so we will prove Kramer's rule. I'll go well next time. Excuse me.
So Monday.
But, I was just saying something. Oh, no, we're not going to get the same formula because this isn't the matrix that I had over there, right? That was the transpose, right? This is A transpose relative to the A that we had earlier, right? But look what happens. Let me keep all the plus terms together. Plus AEI, plus BGF, plus CDH, minus AHF, minus BDI, minus CGE. Compare that to what we had earlier. AEI plus DHC plus GDF plus. Same terms. The minuses. Check it out. So what did we just discover?
Oh, the
They
determinant.
commute. These numbers commute. They're numbers.
Yeah.
So,
So the determinant of A is equal to the determinant of transpose of
in fact, yes, this is the determinant of
A.
A.
That's why you did that. You didn't just make a mistake. You're trying to prove a point.
Oh, yeah, I
That's
guess
really
so.
awesome. Sorry, I'm just. It wasn't an insult. I thought it was awesome. Sorry.
Accidental pedagogy. Yeah, it's always good. But actually, you'll never know. I forget myself if this was on purpose or not. Anyway, this is the cofactor expansion. Now, look, this is the cofactor expansion across the top row. You can do a cofactor expansion across any row or column. Let me show you the cofactor expansion on the middle column. Right, I did top row, let's do middle column. So the cofactor expansion on the middle column, let's focus right here. I'm going to do cofactor expansion on this. So this is the losses gift to us, I suppose. So the signs work like this, guys. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So we use the top row's signs to create the cofactor expansion. Now I'm doing the middle column. So I actually have 2 minuses. I have minus B times the determinant of everything that's not in the B spot, which would be D, F, G, I. And then I do plus B times the determinant of A, C, G, I. All right, and then I do minus h times the determinant of A, C, D, F. You guys with me? So the minuses and the pluses come from this general pattern. All right, and I just have to multiply by the determinant of everything that's not in the column or row in which I'm expanding. So if you're, for example, the H, the last one, everything is not in the third column and second row, but right there. That's another way. Now, so why would you care about being able to do this in different columns? Well, you know, some matrices have lots of zeros, and if they have lots of zeros, then you can exploit a row or column of zeros by doing the cofactor expansion in that row. So let me just go straight ahead and do a 4x4 example. You know, suppose A is equal to 1, 2, 3, 4, 0, 0, 7, 0, and then 1, 1, 2, 2, 3, 3, 4, 4. Oh, we already know that's going to be 0. Let's make it more exciting. Oh, still bad. Look, anytime you have a repeated row or column, you don't need to calculate. You can just go. We know where we started with all this. It was a criteria for invertibility, right? You know, if you have a repeated row or column, game over, 0. So let's make it interesting. Let's make this a 3, and let's make this a. I guess if I just do 2, 2, 2, 2, unless I'm very unlucky, that should be. You know. Okay, so the determinant of A, the way to do this is to capitalize on the column of zeros. That makes for the least calculation, right? And then, so let's see here, I've got plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus. I don't need to write all these out in general. I'm writing this out to help you guys get started, okay? So we're doing the expansion on that column. So you see, I have a minus, a plus, a minus. The only one I actually care about is the 7. So I have minus 7 times the determinant of what? Everything that's not in the 7 column and row, right? So the thing that's not are these guys. And you just keep them in their respective position and put them in this 3x3 determinant, so-called submatrix. You just maintain the submatrix 1, 2, 4, 1, 3, 4, 2, 2, 2. All right, and if I don't see anything particularly nice sticking out at me, what I'll just do at this point is I'll just go back to the top row expansion. That's my go-to personally, and I just write it out. So this is 1 times 6 minus 8, minus 1 times 4 minus 8, plus 2 times 8 minus 12. This is what I used to calculate the 3x3 determinant there. It's just the top row cofactor expansion. Let's see, what's that work out to?
7 times negative 14.
That's minus 2 plus 4.
Oh.
Yeah, it's easy to like.
Positive, negative.
Yeah, I know. Minus 8, right?
Yeah.
So minus 10.
What?
What is it?
It's the answer to life, the universe, and everything. Oh my gosh, I missed calculus theory from back then when everything was good. You remember, right? You remember? Best class ever.
Look, that's an accident, by the way, guys.
No, like when you pause this, you already wrote 42 in the bottom right corner there. Okay.
Oh. Yeah, there's at least
You're calling
at least 1, 2, 3 copies of 42
Really
already.
nice.
It's everywhere, yes.
How did you get the 6 and the 8? And the
Oh, please don't
12?
make an arithmetic mistake.
No, this is right. Please don't do this.
So that is just the cofactor expansion along the top row, the thing I just did a little bit ago.
Oh, so you like,
So the 3
You
by
got
3
the
determinant rule is
determinant
1 times the determinant of this piece, which is
okay.
3 times 2, which is 6, minus 2 times 4, which is 8. Then minus 1 times 2 times 2, which is 4, minus 2 times 4, which is 8, plus 2 times 2 times 4, which is 8, minus 3 times 4, which is 12.
So it's sort of like the chain rule then. You have a 4 by
Basically,
4.
it goes down in dimension every
It
year.
is kind of like a chain rule, yeah, it's iterative. So to calculate the determinant of an n by n matrix, you have a cofactor expansion along the row or column that gives you n minus 1 determinants to calculate, right? And then each one of those, you do a cofactor expansion that gives you n minus 1, n minus 2 determinants to calculate. And then that gives, each one of those gives you n minus 2, n minus 3 determinants to calculate. So as you can see, I'm glad you asked this question, so here's a comment for you. Determinant of A is like n factorial steps to calculate. It's very expensive computationally. I mean, it's a little bit worse than that, right? Because it actually requires multiplications to create those steps. I mean, it's, in terms of straight computations, it's more than that. Look at this, though. I mean, so the 2 by 2 determinant is AD minus BC. That's 2 summands. The 3 by 3 determinant was how many terms? 6, right? That's 3 factorial 6. The 4 by 4 determinant, if I wrote it out in its glory detail, 24. 24 distinct terms. 12 positive, 12 negative. If I was to write out a 5 by 5 determinant, 120 terms. 60 positive, 60 negative. Right? You're like, so is there any other way to write this besides this cofactor expansion? Like, how do you define the determinant really, right? I just discovered it for the 3 by 3, the 2 by 2. Some people, a lot of standard books will pretend that the definition for the determinant is terms of cofactor expansion. I don't think that's the truth, though. For me, the definition of the determinant is as follows. Here we go. The determinant of A is equal to a sum. I1, I2, in equals 1 to n of epsilon I1, I2, in. A1, I1, A2, I2, an, where epsilon I1, I2, in is completely antisymmetric. And, epsilon 1, 2, 3, n is equal to 1. So that, folks, for me suffices to give a concrete and explicit determinant that defines the determinant for an arbitrary n by n matrix. It's a completely general formula. So what I'm saying is you basically add over this antisymmetrized combination of columns. Here, I'll show you how that works in the 3 by 3 case. So I'm saying the determinant of A is equal to the sum over ijk equals 1 to 3 of epsilon ijk, a1i, a2j, a3k. Excuse me, guys. My notes go. Now, So this epsilon ijk, what I'm telling you is it's defined by like epsilon 1, 2, 3 equals to 1, right? And I said it's completely anti-symmetric. What that means is if you turn over any two indices, you get a minus. For example, epsilon 2, 1, 3, minus 1. So epsilon 2, 3, 1 is 1 because I just flipped the 3 and the 1 here, right? Let's see here. What else can you get? Epsilon 1, 3, 2, minus 1. Epsilon 3, 1, 2. I don't think I had that one yet. 3, 1, 2 would be 1. Each one in this list, I'm just flipping a pair of indices to get to the next one and changing the sign, right? Can you think of any other distinct triples? I've got 1, 2, 3, 2, 3, 1, 2, 3, oh, excuse me, 2, 1, 3, 2, 3, 1, 3, 2, 1. Okay, what would that be? Epsilon 3, 2, 1.
Negative 1.
Negative 1. Okay, so what this then becomes, right? If you look at what is the sum? Actually, it's epsilon 1, 2, 3, A11, A22, A33, plus epsilon 2, 3, 1, A12, A23, A31, plus epsilon 3, 1, 2, A13, A11, A31, A32, minus epsilon 3, 2, 1, A13, A22, A3, 1, minus epsilon, oh, I'm sorry. I don't need to write the minus epsilon. I'm an idiot. Well, I'm thinking of epsilon 2, 1, 3. Cheat here. A 1, 2, A 2, 1, A 3, 3, minus epsilon. Let's see what's the next one. 1, 3, 2. So A 1, 1, A 2, 3, A 3, 2. I don't know why I'm actually writing this out. I should just tell you it works. You can believe me. Those weren't supposed to be there. They're supposed to be plus or minus 1. See, if you look at right, and then if you go back to our silly trick from earlier today, right? Then you can see that you got like a plus on the diagonal product, right? See these guys? And then the A1, 2, A2, 3, A3, 1. Right here. And then the plus from A1, 3, A2, 1, A3, 2. And the remaining 3 would be the net minuses, just like I said. Yeah.
Why is there a random minus A32 then?
Oh, that's a typo.
Not typo.
That should just be times. All right. How many of you guys have seen the determinant before? Right. Where did you see it? Calculus 3. There we saw what?
Oh, we also saw it in algebra, but we probably don't remember.
That's likely true. Calculus 3, we tell you this thing like A cross B, right? It's the determinant of what? I, J, K. We put hats on them, or we make them
And
bold.
then we made the vector 1.
Yeah, this thing, right?
Yay.
So, what this actually anyway, I have a homework problem which makes this a little bit more careful.
And it's basically nice and normal, or at least a vector.
Let's So, for example, A cross B dot, well, I can't, if I start into this, I'm going to solve your homework problem, I better not do that.
Oh, no.
That'd be fine. That would be.
Just keep going. Don't stop, don't stop.
In the homework, I replaced this with a more careful formula. I say what they really mean by this is the sum, j equals 1 to 3, of the determinant of E1, E2, E3, A1, A2, A3, B1, B2, B3, and then you put that with EJ. That is
That's just the matrix version.
actually but anyway, that's anyway, I have some problems about that where you actually prove things like, for example, I call this thing, I give this a name, I call this T of A, B, right? And one of your homework problems is to prove that T of A comma B dotted with C is equal to what? It's equal to the determinant, as it turns out, of, I guess we could do C, A, B. I'm sorry, I'm putting vector signs on stuff all of a sudden. But, excuse me. All right, let me regroup for a second here. So up to now, I've pretty much just shown you formulas for how to calculate determinants, right? There are tons of tricks, by the way. There's properties of determinants which are useful for calculation. One of them is if you switch any row or column, you get a minus, all right, from what you had before. You can also do row reduction, like if you keep track of the signs, there's a way of doing determinants using row reduction. Another fun fact about determinants, the determinant of block matrix. For example, like this. If I have blocks, say M1, M2, so forth. Suppose I got K blocks. So, and 0 off the blocks. So a block diagonal matrix, something very wonderful is it turns out it's the determinant of the blocks multiplied together. So one very nice case of this, of course, is if the matrix is diagonal, the determinant is just the product of the diagonals. Okay. But there are other results. For example, if you have the determinant of either an upper triangular or a lower triangular matrix, again, just the product of the diagonals. So those are some special cases, like, you know, if you ask me what's the determinant of 1, 2, 3, 4 stuff, it doesn't care. I don't care what the stuff is. If it's 0 below the diagonal, the answer is 1 times 2 times 3 times 4. Simple as that. So diagonal matrices or triangular matrices, upper triangular or lower triangular, you just calculate the determinant by multiplying the diagonals. It's also something that turns out to be true. I have undoubtedly left something out in terms of how to calculate them. Let me turn the leaf here to a different question. What are they? What are determinants? What do they mean? I mean, we know that them not being 0 reveals what? That the matrix is invertibility. But it's more than that. But you know, you could say, well, 2 is not 0, but minus 2 is also not 0, right? So why did I make the determinant 2 and not minus 2 for a given one, for example? Like, what's the significance of the sign of the determinant? Okay. Now, this homework problem partly reveals it to you. If this is A cross B dot C, if you had count 3 before, you might recognize this as a triple product. This, of course, is what? This is the volume, right? This is the volume, actually, of the parallel pipette with sides A, B, C. Well, I mean, it's plus or minus the volume. I mean, it could be minus, right? So what I'm telling you is the meaning, the specific choice, all right, of the formula we did to not minus it, and not some scalar multiple as well, right? Because if you think about it, let's be more specific. If I have AD minus BC, right, not equal to 0, or if I, generally speaking, have the determinant of A not equal to 0, then doesn't that also imply that any non-zero scalar k times the determinant of A is not equal to 0, right? So you can ask the question, why did I choose k equals to 1, basically? Right? What's the significance of k equals to 1? What does that mean? And the answer is simply volume. And it also it gives you a sense of orientation. So for n equals to 2, if I look at the determinant of, say, vector A and vector B, two component vectors, right? Then this is equal to the area of the parallelogram with sides AB, provided the picture looks like this. In other words, I get B from rotating counterclockwise from A. So the second thing is a counterclockwise rotation of the first vector into the second. If that's the case, then the determinant is positive. On the other hand, everything else being the same, if I flip the roles of A and B, I get a minus, right? So, for example, like the determinant of, let me just draw a picture of one where it's oppositely arranged. Let's see, let's put A, let's say A is 1, 2, right? And B is, 2, 0. Right, so if I calculate 1, 2, 2, 0, what do I get? Yeah, negative 4. Right, and if you look at the parallelogram here, does it have area 4? What's the base? 2. What's the height? 2. Base times height, parallelogram, 4. Not an accident. So, you want to calculate the area of the parallelogram? You just stick the sides of the parallelograms as vectors into a 2x2 matrix, calculate the determinant, bam, area.
So would you say it's the absolute value of the determinant?
Yeah, the area is always the absolute value. The plus or minus, again, reveals whether or not B is obtained from A by doing a counterclockwise rotation. Like that. That's the notion of orientation, right? That orientation in the plane has to do with clockwise versus counterclockwise angles. For 3, so if I wanted to calculate the volume of, say, A, B, then suppose, so it's parallelogram, then suppose I have another one, like that. Sorry, my picture's not that great. So I'm trying to draw a parallel like that. Oh, I failed. Sorry. So C could also be put back here, The volume of this shape with sides A, B, C would be the determinant, plus or minus the determinant, right, of A, B, C. The signs, in this case, plus or minus, again, are tied to the question of orientation. Right, so definition for our 3, we can say that a set of vectors, say A, B, C, form a so-called right-handed triple. Right-handed triple if the determinant of A, B, C is greater than 0. What that means, guys, okay, here's what that means. If I have vector A, right, and I have vector B, and they lie in some plane, all right, I can do the cross product of those vectors, if you know what that is. Some of you had physics, some of you don't. If you haven't, you'll learn what you need to in the homework set, though, to spare. I don't anticipate in the third test that you're going to be sitting around doing this. Not likely. Okay. So Anyway, but for the sake of our collective understanding, A cross B is a vector that goes up, right? So A cross B is a vector which is perpendicular to A and B, and in this case points out in the plane. So the formula I just erased was that the determinant of A, B, that was that the determinant of A, B, C, like so, was equal to, in fact, A cross B dot C. In other words, the determinant of three vectors stacked together gives you the so-called triple product. So geometrically, what does it mean for this? What does it mean for C, the dot product of C with A cross B? What does it mean for that to be positive? It simply means that C, if you attach it to the plane, right? It means it's on the same side of the plane as A cross B. If that dot product were negative, that means C is below the plane. It's on the opposite side of the plane as A cross B. So if the forms right hand triple, if the determinant of A cross B, ABC is zero, is greater than zero, that's what we mean for it to be right-handed. It's for for A cross B to point in generally the same direction as C. Okay. Now, if you add orthonormality to the mix, that means that the vectors are perpendicular and that they have length 1. We'll talk about that later. When we're in that context, we actually would insist that the vector C is in fact the cross product of A and B. But that's a slightly more rigid structure that we're not to yet. So if you ask me in a nutshell, what is the determinant? My answer to you is that the determinant is volume. The determinant is the volume of the n pipette, which is spanned by the columns of the matrix. And of course, if you think about it, that's naturally tied to the question we started with, right? Because what would happen if your n volume wasn't really a genuine n volume? What happens if two of your edges are in fact collinear, right? For a parallel pipette, if two of your edges are actually collinear, it's not really a parallel pipette, it's just a parallelogram. Or worse yet, a line, right? So what's the volume of a two-dimensional area? It's 0. Just like the determinant of the matrix, which would be correspondingly formed, would be 0 if it's not invertible. So anyway, this is why determinants come up in Calculus 3, is because the determinant reveals for us whether or not the volume is preserved under transformations at the infinitesimal level. You look at the determinant of the linearization, which is the Jacobian, and it tells you much about transformations. Oh, assessment data, yes. Well, you can cut it off now if you want. Thanks.